So welcome to our little course on deep learning for 3D geometry. So just to get started, I just want to tell you a little bit about who your instructors will be for today. So I'm Daniel. I'm a professor at Brown University just down the road in Providence, Rhode Island. I am interested in many things at the intersection of graphics and machine learning. I do a lot of 3D shape and scene generation and dabble in program synthesis as it pertains to those problems. And this, I'm actually very excited. This is my very first in-person SGP. I did another one of these graduate school things back during the COVID remote everything era, but it's great to be here and actually see the people who are in the room. Zoe?
Yes. Hello, everyone. I'm Zoe. I'm a first-year PhD student at CMU. And previously, I was an undergrad here at MIT, so it's nice to be back here. And I have pretty broad interest in geometry processing, but I specifically like things that have kind of cool math in them. And so I've worked a bit in the past on interesting shape representations. And I also really am interested in discrete differential geometry. And this is also my first in-person SGP, so it's great to be here.
All right. Okay, let's get hooked up. Great. Okay. So yeah, I also want to, we've told you a bit about ourselves. I'd like to learn a little bit about who all is in the audience. So I'd just quickly raise a hand if this is your first SGP. Wow, lots of newcomers. Great. It feels good to be in good company. If you are a graduate student, okay, good number of folks. Do we have any undergrad students here? Nice, love to see it. Anybody else who doesn't fit those categories? Yay, excellent. I love it. Anybody here done any geometry processing work before? Courses, research, okay. Makes sense, we're at SGP. Anybody done any deep learning work here before? Okay, maybe a little bit less, but still a good number. How about things at the intersection of deep learning and geometry? We've got, okay. So yeah, so this will be a fairly, I'm kind of trying to keep things fundamental here. So some of you may be, may have seen some of this before, but I wanted to design something that was accessible for everyone. All right, so why are we doing this course? Why are we all here today? I mean, it's no surprise, right? Deep learning has basically found its way into the problem-solving toolbox of essentially every field of computer science by now. This includes computer graphics, and geometry processing is no exception. So you might have been seeing a lot of papers coming up recently at conferences like SIGGRAPH that have neural in the title, like neural subdivision, or neural cages, or neural Jacobian fields, or even at this very conference on Monday, something called one Lipschitz neural distance fields. What is that all about? And so I think everyone getting into geometry processing should have at least some basic understanding of how this thing called deep learning is used in the field. And so when Zoe and I were thinking about how we were going to put together this course, what we came up with was basically there are two interpretations, at least, of this title, Deep Learning for Geometry Processing, 3D Geometry. One is to interpret this as we're talking about the practice of using neural networks to solve prediction problems that involve 3D geometry. But there's another angle where you could actually talk about the process of using neural networks as a representation for 3D geometry itself. And as it so happens, this is the structure that we have decided to use to break up the course. So for the first 40-ish minutes or so, I'm going to talk about this first topic. We'll have a quick 5-minute break for people to get up, stretch, use the bathroom, because I know we've all been drinking coffee, and give your brains a rest. And we'll come back for the next 40 or so minutes when Zoe will talk about this second interpretation of the course title. Okay, so just real quick, some basics about what the goals of this course are. Hopefully, after you've been through this course, you'll leave it knowing something about the kinds of problems that deep learning is being used to solve in geometry processing. And one of the things that I'm going to present that hopefully will be useful to some of you is some kind of a framework for organizing those problems. So when you see new papers come up, you can think about where do they fit. You'll understand some of the unique challenges that apply in applying deep learning to 3D geometry, why it's a little trickier than in some of the other fields where it's being used. And understanding both how and why, and maybe why not in some cases, you might represent 3D shapes using neural networks. And finally, I like to leave a lot of references. These slides are going to be available online, a lot of links and references so that you know where to look if you want to learn more about any of the stuff that I'm talking about today. I sometimes think of myself as a systems person, so if I'm telling you about my goals, I have to tell you about the non-goals of this course as well. So this course will not really dive deep into the methodological details of lots of recent papers. This is sort of a broad survey. It's kind of intentionally designed that way. We don't have a lot of time, and I want to make sure it's accessible. I'm not going to teach very much about deep learning in general. This is a course about the application of deep learning to geometry processing. And specifically, this is not really going to teach you how to write PyTorch or TensorFlow or insert your favorite deep learning framework here programs. Probably no surprise to anybody. All right, great. So let's dig into this first topic about using neural networks to solve prediction problems that involve 3D geometry. And so first of all, I need to at least have some groundwork for what the heck is this deep learning thing so we can all have the same language to talk about it. And I like to think about it, really, deep learning is what is it all about? It's really just all about function approximation. Hopefully everybody here knows enough math to where that's reasonably comfortable to talk about. What we're trying to do is we're trying to compute some function. We have some f of x we want to compute, produces y's. But maybe we're in a situation where f is just too complicated for us to write down ourselves. Like maybe we want something that takes f of an image and tells me that that thing is a cat that's in that image. I don't know how to write that program by hand. If you were Marvin Minsky here at MIT in the 60s, you thought you could just give this problem to a bunch of undergrads for a summer and they'd solve it for you. But it turns out it's actually a lot harder than they expected. So a neural network is something we can use to help us with this. A neural network, really, it's just a parametric family of functions, some family of functions that has some parameter theta. And we can optimize those parameters to solve our problem if we have some data set of examples. So I have a big data set D of these XY pairs, and I can try to find somehow a setting of this theta that minimizes some notion of the difference between the output of this function when run on the x's and the y's that it is supposed to produce. Basic idea. So most problems in deep learning, you can characterize them by the answers to a few different questions. What type of prediction problem are we trying to solve? So basically, I'm going to relate all this to that framework I just gave before. So what is the function that f of x is trying to compute? How are we representing the data? So what form do the x's and y's take? What neural network architecture are we using, which really just means what parametric family of f thetas are we using? And then finally, how are we going to train the network? Training just meaning what is the optimization algorithm that we use to solve this particular optimization problem that I posed before. Now this last thing, I'm not really going to cover this today. This is kind of part of that deep learning in general that we don't really have time to get to. If you want to learn more about this, there's a lot of resources out there. One example, just to plug something I was involved in designing, you can take a look at the course notes for Brown's deep learning course. So these are the three questions we're going to dig into in the first part of the course. And let's start with the first one. What type of prediction problem are we trying to solve? Right? What do we want to compute? What function are we computing? So I am going to introduce this by providing a taxonomy of prediction problems, sort of a way of kind of categorizing, breaking down the kinds of learning problems that are out there in geometry processing. This is going to be sort of a framework for you to mentally organize these problems in your head when you see new papers come up online. I do want to give a caveat. Some of you may have seen this quote before, often attributed to the statistician George Box. All models are wrong, but some are useful. What I mean by that is that not every single deep learning for geometry paper you might find is going to fit perfectly neatly into this framework, but I think enough of them do for this to be a useful way to think about things. So let's dig into it. So if we start with sort of the root node of this hierarchy, this sort of encapsulates every possible prediction problem you might be interested in. The first split we can make is between what I'll call analysis and synthesis problems. So if we're talking about analysis, we're talking about we are trying to compute some property of existing geometry. So in our little f of x equals y setup, x is some geometry and y is not. Y is some other quantity we want to compute. Whereas in synthesis problems, we're trying to generate new geometry. So in this case, the y is geometry and the x may or may not be. We'll see examples of that later. If we dig in, we're first going to dig into the analysis side of this tree. We can divide this into what I like to think of as global analysis versus local analysis. So for these global problems, we're trying to take our geometry, our input shape, and compute some sort of single value that summarizes that shape. Maybe for whatever reason we have some function, we pass in the Stanford bunny and it tells us 0.5. That's to be contrasted with these local analysis problems where the y that we're trying to compute is actually some sort of pointwise signal across the entire shape, like this example that I've shown here. Okay, so let's look at some examples of these different kinds of analysis problems, just to make it a little bit more concrete. So when we talk about global analysis, right, sort of summarizing the entire shape, what are the concrete kinds of problems that people want to do this with? So the most obvious, the most kind of widespread version is classification, right? I have some input shape, I pass it into my function, and it gives me some sort of distribution over the probabilities of what type of thing this is, right? Usually, but not always, there's some finite vocabulary of possible classes that have been provided to this function in advance. And hopefully, if we've done a good job of optimizing the parameters of this function, it'll tell us that the most likely category is airplane for this particular shape. Other examples we might see, here's a more interesting, more complicated one, the problem of canonicalization. It is a coincidence that all of these start with C, as we will see. So canonicalization is a problem where I might have a whole bunch of shapes. In this case, they do happen to be of the same type, the same class. Basically, this function would respond the same way to all of them. So here we've got a bunch of chairs. And what I would like my function to do is when I pass these shapes into them, it will give me as output, the y in this case, is going to be a transformation, a rotation plus a translation, such that if I then were to take the input shapes and pass them through that transformation, I would end up bringing all of these chairs into a mutually aligned coordinate frame so that I know they are all, sort of the up direction and the forward-facing direction for these chairs is all the same. Okay? And then another example that we're starting to see a lot of these days is captioning. So the case where I have some input shape. Here I've just represented it by a couple of different views. And my function is going to do something like produce a string, a text string that describes what that shape is. In this case, a 3D model of an armored character with purple horns and spikes on the back. Okay, so hopefully that gives you some concrete ideas of what kinds of prediction problems we might be interested in. Now if we switch gears and think about local analysis problems where we're trying to predict some sort of pointwise signal across a shape, why might we want to do that? What are examples of problems where people actually do that sort of thing? Probably the most well-known, widely spread instance of this is segmentation, where I have my input shape, in this case, the 3D scan of a person, and my function is supposed to assign a value to each point on that shape, which tells me what part of the person's body is this. So I'm not showing a color key, but in this case, we'd have red would be the head, and green would be the torso, and so on. Another one that can be quite useful is normal estimation. So suppose I have a big old cloud of points that maybe I got from some sort of a 3D scanner, and I know that this thing represents some continuous 3D surface in the world, but I don't actually have that in the data. I just have a bunch of disconnected points. So I don't actually know what are necessarily the normal directions, basically the outward-facing direction from the underlying surface. So I might like to have a neural network which can take this cloud of unoriented points and tell me what direction the surface is pointing at each point in that point cloud. And in this case, I've just done the standard thing of coloring each point where RGB correspond to the XYZ coordinates of where that normal direction is facing. So clearly green is mostly facing toward our view direction. Now some more interesting, slightly exotic things you can do. So you can actually frame problems like geodesic distance calculation in this framework. So in this case, we're going to extend our input a little bit. Our x is going to be a shape and a point on that shape. So here I've illustrated that point with this little blue dot here on the chest of this armadillo model. And what I would like my neural network, my function, to do is to produce this field of distances across the surface, which basically tell me how far away is the closest, basically, what is the distance of the path that I can travel from this original point to, say, this point, the closest distance, like the shortest path I can travel to get there, how long is that path? Now, this is not a problem. I know I mentioned before that we like to use this deep learning setup for solving problems where the function is too complicated to write down by hand. In this case, that's not true. There are plenty of classic algorithms for computing geodesic distances. But one of the other things that we'll often want to use learning for is to accelerate or amortize something that can take a long time to compute. And so in this case, this neural network can compute this result faster sometimes than classical algorithms. And another example that often comes up is shape correspondence. So again, in this case, slightly different input case. We're going to have our x is going to be two shapes, not one. And if we pass these two shapes through our function, what we'd like to have as output is this, again, continuous field of values across the shape, such that basically where on these shapes there are the same color, that indicates that these shapes are roughly in structural correspondence with each other. So for example, we have this kind of pink color on both of the front left feet of these quadrupeds. And the way that this works typically is that there's some sort of field of feature vectors that are produced across each of these shapes, and the affinity between them is determined by some sort of distance, like a dot product or a cosine distance between them. Okay, so that's my kind of 10,000-foot overview of the analysis side of deep learning for geometry. Now if we switch gears and talk about synthesis, so no longer trying to answer questions about existing geometry, but produce new geometry, once again, I think we can subdivide the synthesis category into a couple of subcategories. And this is kind of a popular division that we see all across generative modeling these days, not just in geometry, is unconditional versus conditional synthesis. So in unconditional synthesis, we are just trying to generate a shape, typically from some distribution of shape. Unconditional comes from an unconditional probability distribution of shapes we are sampling from. And so in the kind of f of x equals y framework, we can think about this as x is just random numbers. We give a random number to this function, and it produces some shape. Now with conditional generative modeling, conditional synthesis, we still have random numbers. We're still sampling from a conditional distribution of possible shapes, but there's also something else that's provided as input to guide what that sampling looks like. And I also think it's meaningful to talk about the something else as lying along a spectrum, where we can either be providing a lot of cues about what the output shape should look like, in which case our conditional distribution we sample from is very low entropy, or it can be sort of a vague clue about what the shape should look like, in which case we have a very high entropy distribution. And you can fall anywhere along the spectrum. All right. So some noteworthy examples of unconditional shape synthesis. This is just, this is not authoritative. This is just me picking out a few things that I think are interesting, sort of milestones along the way that are worth looking into more, perhaps, if you're interested in this. So there's this paper from probably about 5 years ago now or so called IMNet, which is one of the papers that introduced, about 4 papers came at it around the same time, which introduced this idea of representing 3D shapes using neural networks, which Zoe will be talking about later. And in particular, it showed how to also use a neural network to generate this representation. And it allowed you to do some very cool things like having a vector of these random numbers that control the output, and you can basically smoothly vary these random numbers and start to see smooth variation in the output shapes that you would get as a result of running this function. So we can sort of smoothly navigate the space of, say, possible cars that could be generated. More recently, probably everybody in this room has been hearing tons of things, perhaps tired of hearing things about diffusion generative models. This has also found its way into geometry processing. This is one of, I think, perhaps the first paper that I remember applying this type of generative modeling to 3D shapes. One of those things that, again, I'm not going to have a lot of time to talk about today, about diffusion models and what they are. Happy to talk about that offline if people are interested. And then actually, which I believe was just presented at CVPR last week, this paper called Mesh GPT, which is a very different way of looking at synthesizing geometry, basically having some process that step by step produces vertices and the faces that connect them. Not the first paper to do this, but kind of a significant step forward in the scale of geometry that could be plausibly handled. And arguably, this could produce meshes that look more like the kinds of things that someone sitting down and working in a tool like Maya or Blender might actually produce. So, interesting stuff. All right. So, thinking about moving on to conditional shape synthesis, I want to lay out these examples again along that axis that I presented earlier of kind of low entropy, where we're really providing a lot of cues about what the shape looks like, down to really high entropy, where we're not providing many cues and we could get many shapes as output. So, if you think about things that lie along the very, very low entropy side of the spectrum, we have the problem of, say, taking points and trying to infer a surface from them. So this sort of point cloud conditional shape synthesis. And there's a bunch of different methods for doing this. I'm going to leave a couple references here. This paper about convolutional occupancy networks learns a model that does this on a shape category by category basis. Or in some cases, they actually apply this to entire scenes. So essentially, the idea is they have a big cloud of points, and their model is learning something about the typical structures that occur in shapes, so that if it sees, perhaps an incomplete cloud of points here or there, it knows that, well, I know this is a chair, and so chairs are typically in this empty region would be filled in like so. There's another approach to doing this. An example of that would be deep moving least squares, which doesn't really look at the sort of global structure of the shape, but kind of just looks at local pieces of the point cloud. And regardless of what shape that thing makes up, it's just trying to figure out how would I take this local patch of points and figure out how to kind of wrap that with the surface. So you can imagine, maybe you don't know as much about what the shape looks like, but you could apply this to any kind of shape whatsoever. So there are some trade-offs there. All right, moving down the spectrum of gradually increasing entropy, we have the problem of going from images, or even a single image, to a shape. This is higher entropy because when we have, say, a single image, we only see the front side of this chair. We actually have no information, at least no direct information, about what the back side of that chair looks like. So once again, there's a paper that was fairly seminal in this area called Pix3D from here at MIT, which is, again, learning from a large data set of examples to say, well, I can't see the back of this chair, but I do know what 3D chairs look like in general, and so I can use that information as encoded in the parameters of this function that I've learned to infer plausibly what the backside of this thing might look like. And nowadays, we have systems that can do this not just for single categories of shapes, but for any old shape whatsoever. This is an example from, I think, just earlier this year that purports to take a single image of essentially anything and produce a reasonable 3D reconstruction of what it looks like, not just its shape in this case, but also its surface appearance, or at least its diffuse albedo, its color. All right, and then sort of lastly, I think along this spectrum of entropy, really the highest entropy is text to 3D shape, right? A natural language description, people always say a picture is worth 1,000 words. So if I only give you like 10 words, I'm not really specifying that much about what the 3D shape should be. So we have some very early work. I think this is from close to 10 years ago now, which takes relatively simple descriptions of shapes, including their surface appearance, a little bit about what parts they're composed of, and produces an okay 3D shape output. Nowadays, there's been a lot more work. Obviously, people have seen the explosion of interest in text-to-image generative models, and so some of that has sort of bled over into text to 3D. So we have things like OpenAI's Shapey, which I think produces a lot more evocative outputs now. So I'd argue this looks more like a donut with pink icing than the output above looks like the description that was given for it. All right. So yeah, this is kind of the basic top-level taxonomy that I like to use when I'm thinking about, okay, I see a new paper. It's got neural or deep learning in its title, and there's 3D shapes in the teasers. What is this paper doing? This is kind of like the first level in which I will try to bin things in my brain. All right. So that's just kind of a quick overview of what kinds of problems we might be interested in solving. Let's talk a little bit more now about what we're going to use to represent the data that this network is both consuming as input and producing as output. And this is where I think things get really interesting with learning for geometry, because in other fields where deep learning has been taking over as a major or the predominant problem-solving tool, there's often one clear answer. So if you are a language processing researcher, you are going to represent the input to your network and the output as a sequence of tokens, right? There's some process called tokenization, which will take a string of text and turn it into a series of discrete entities, which can then be, the data that you operate on. If you are a image processing or a sort of a 2D computer vision person, the answer is again pretty obvious, right? The standard way that we represent images on our computers is as a discrete grid of pixels, right? A 2D regular grid. Easy, done. But as it turns out, there are many ways to represent 3D geometry. It's something about that extra dimension, right? Once you have a signal that's now represented at some points in 3D space, things get a lot more interesting. So let's think about what are some of the ways that we can represent 3D geometry. Just feel free to shoot up a hand. What are some of the representations of geometry that we know of? Yeah. Triangle meshes, great. So meshes, we use a lot of those in graphics. What else? Yeah. Implicit surfaces, okay. Yep, that's also something that you might use for learning. I think I saw another hand in the back, yeah. Voxels, okay. Or some sort of, these things, as we'll see, can be related. They can both be represented as grids. Any other things people are aware of? Yes, down here. Functional representations. You want to unpack that for me? SDF. Okay, SDFs, which are, I'd argue, sort of a subcategory of implicit surfaces, yeah. But implicits can be represented other ways too, yeah. Point clouds, there we go. I was waiting for that one. It's kind of like the lowest common denominator in some ways. Point clouds. Also, I apologize for my terrible handwriting. Yes, up here. Somebody's getting ahead of me. Yes, neural networks. Yes, so we will talk about this one. Zoe will talk about this one later. Anything else that we think we're missing here? Yeah. Procedural descriptions. There we go. So procedures, we'll talk about that a little bit. This is something that's near and dear to my heart, but I do have to make this course be cover the things that I think are most important for everyone. So I could spend an hour and a half talking about procedures, but I won't today. Yes, back there. BREPs, also very related to procedures, because as we will see, I don't know why I decided to capitalize that. Procedures in CAD modeling programs often produce BREPs, so those are tightly coupled. Okay, I think we've got a good sampling of them here. Obviously, there's a whole exotic long tail of geometry representations that have been proposed, but we've got the gears turning. All right. So if there are so many ways to represent geometry, but I talked about before that in other fields there's just the one obvious representation that we use for learning. So you might be thinking what we really should be searching for is the one representation to rule them all. That's the one that we can focus on that. All of the research efforts can be focused on how do we do deep learning on that representation. And for both better and worse, I'm here to tell you that that's not how things are going. And I think there are good reasons for this. There are good reasons to use different geometry representations for learning. So I'm going to go through some of the representations, actually I think most of the representations that we just came up with on the previous slide, and talk about why you might want to do learning with that representation. So point clouds, first of all. These are very easy to acquire. If I have some sort of sensor, perhaps a depth sensor, it's easy to get these from the real world compared to other kinds of representations. And so if I'm in a field like vision or robotics, I have some sort of autonomous agent that's supposed to make decisions based on what it's observing. This is a really good representation for me to work with if I want to teach or have my agents learn using deep learning how to make those decisions. They're going to get these point cloud observations. Easy representation. As we also saw before, when I talked about conditional synthesis, I might want to use learning to actually convert point clouds into other representations. So we better have a way to somehow do learning on point clouds. Triangle meshes. These are arguably the most common representation in graphics, so there's lots of data available there in mesh format. We'd like to be able to work with that, so we should figure out how to do learning on meshes. Also, meshes compactly and explicitly represent the actual surface of the object, unlike a point cloud, right? Point clouds, we just have discrete samples of where the surface is. So if you really want to do what in geometry we'd call intrinsic analysis, you want to analyze some property of what's happening on the surface, this is a great representation for that. Something we actually didn't come up in the that last little slide where we're taking notes is images or multiple views of an object. This is another way that you can represent geometry. And the reason why this might be nice is that folks in 2D image processing and computer vision have spent a bunch of time developing neural network methods for processing 2D images. And so we might just be able to basically co-opt a lot of their work to analyze or synthesize 3D shapes. Somewhat similarly, we have 3D grid representations. I know somebody mentioned voxels, where basically every cell in the grid describes whether there is shape there or not. Someone also mentioned SDFs, or implicit surfaces, where those grid cells might store some other number that tells me something about where the surface is. And Zoe will be telling us a lot more about how those work in the next part of the course. But if we have 3D grids, here I'm showing the same chair represented with different resolutions of grid. again, a 3D grid is not too dissimilar from a 2D grid. And so while we can't exactly reuse the learning machinery that the folks in 2D vision have been producing, we can adapt it relatively straightforwardly. There's relatively straightforward extensions. And then finally, these CAD representations, things like procedures or BREPs, they give me an infinite resolution representation of the surface. There's no loss of detail from discretization or anything like that. And so if I want to deploy learning within the context of, say, a CAD modeling tool or a procedural modeling tool, this would be a good representation to learn on directly, so I'm not sacrificing any detail or accuracy by converting to something else. OK, so that's just the spiel I wanted to give about representation. Very interesting problem in geometry processing compared to other fields. So let's wrap up the last 10 or 15 minutes or so talking about this problem of what neural network architecture we want to use. What is this? How are we scoping out this parametric family of functions that we are going to then try to learn? OK, so for this, I'm going to give you a possibly overly simplistic, reductive, but I think actually very helpful way to think about what a deep neural network is. Just kind of scraping away all of this stuff about TensorFlow code and PyTorch and all this stuff that doesn't really matter. At its essence, a deep neural network is a composition of functions, which the term of art in the field is layers instead of functions. So here I have G composed with H composed with J. And some of those functions happen to have parameters, or again, as the folks in the field will call it, they'll call them weights. So here my function G has some parameters theta 1, and my function J has some other set of parameters theta 2, but this function H sitting between them doesn't. Not all of them have to have parameters. Another term you might hear thrown around is that the functions in this chain, which do have parameters, will often be referred to as learnable layers. Right? They're the layers which are learnable because they have parameters which can be optimized. Speaking of optimizing parameters, the third thing, which is true of a deep neural network, is that the gradients with respect to all of these parameters are well defined, so that we can optimize these parameters with first order optimization methods, something in the gradient descent family. Really, I think these three things are just get at the core of what a neural network is. And there's lots of other gobbledygook on top, but I think this is at the core of it. All right, so this is the one slide where I'm going to do the most talking about deep learning in general, because I just want to make sure that we're all on the same page about this so that we can appreciate some of what's going to come later, is I want to kind of introduce the three primary types of learnable layers that typically exist in these networks or these function compositions. And there really are three of them these days. Obviously, there's a whole zoo that have been proposed, but these are the ones that have sort of stuck around as the most useful. And so the first one are, you might see both of these terms used, fully connected layers or linear layers. What is this? Well, it's just the output y is related to the input as wx plus b, where w is a matrix and b is a vector. And w and b are the parameters that can be optimized in this case. So why this is called fully connected is because if we think about the entries of these input and output vectors, we think about x and y as vectors or sets, every element of the output is going to be linearly related to every element of the input. So there's sort of a data flow connection between every pair of elements. That's where fully connected comes in. Another term that you'll want to be able to keep in mind is when you have multiple of these fully connected layers that are composed together in a chain, and in between each pair of them, there is some parameterless nonlinear function. That has another name in the field. It's called a multi-layer perceptron, or an MLP. It's a weird mouthful. Where that comes from is sort of a historical note. It's not super important for this context, but happy to talk about that later. You might have noticed that I have this little asterisk here next to linear. It's because I'm always a little bit miffed about this. These really should be called affine layers because there's a scale and a shift. But anyway, terminology gets set in stone. There's no way you're going to get all of the contributors to PyTorch to decide to rename this affine instead of linear, as much as I wish they would. OK, the second main type of learnable layer is, and this is, I know, a bit hand-wavy, something that looks like convolution, right? Convolution has a very specific formalization within sort of the signal processing literature. Not everything that is referred to as a convolution in deep learning actually fits that characterization. but it's kind of like convolution. So what do I mean by this? I mean that, okay, now we're not going to think about our inputs and outputs as vectors. We're going to think about them as some sort of a set. We still have these elements, a bunch of x's and a bunch of y's, but now we can think about them as a set. And in particular, in this case, it's going to be a set that exists in some sort of space. So we can think about, for any particular input xi, we can think about where that sits spatially compared to all of the other inputs. And we can imagine that we can define some notion of a local neighborhood. So all of these that are kind of purple colored are in the local neighborhood, and all of these other ones are not, because they're too far away under some notion of distance. And so armed with this way of thinking about our data, then this sort of convolution type layer is basically saying every element of the output is going to be a function of this local neighborhood of the corresponding input. And that function is usually, it's depicted as a sum over all of the elements that are in the input of some parameterized or learnable function of xi and the neighbor, where the neighbor could also be itself, right? Because xi is within its own local neighborhood. Now, most of the time, for most convolution-like operators that are in the literature, most of the time this function is really just a weighted combination of the local neighbors. So it's just a weighted sum of the xj's, where the weight, again, these are the learnable things. The weight is a function of the sort of the relationship between xi and xj. In some cases, this might just be a fixed constant set of weights. In other cases, it might be a learnable function. I mention often but not always, if you want sort of a noteworthy exception where this is not the case, you can look up message passing neural networks are a variant of this, which is convolution-like but don't quite fit the weighted combination formalism. Okay. And finally, the last primary type of learnable layer, and arguably the most complicated, is attention, which is this mechanism that gets used a lot in this type of neural network called a transformer, which you might have been hearing about a lot, like the T in ChatGPT is transformer. Again, also a terrible name, right? Like every neural network transforms its input. Like why does this one get to lay claim to? Anyway, so what is attention? Well, it's this mess, but what we can see is that basically every element, again, of the output is a weighted combination of, in this case, every element of the input. So there's no sort of spatial localization here. Every element, so in some sense, it kind of resembles the fully connected layer this way. However, how these weights are computed is a little bit special. So we notice that I have these three matrices, Q, K, and V. And so every element of the input first gets linearly transformed into what's called a query vector, a key vector, and a value vector by being multiplied by these three matrices. These matrices are optimizable or learnable parameters. And then every element of the output is just a weighted combination of these value vectors where the weights are given by the affinity or the dot products between the query vectors and the key vectors. Okay, that's mechanistically what's happening. Why do we do this? The intuition here is that the weights represent how much attention each element pays to every other element based on their distance in this learned feature space that gets induced by the mappings of Q and K. That's the idea. That's where attention comes from. I am also actually eliding some details here. Typical formulations of attention look a little bit more complicated than this. This is the sort of intellectual core of it. I left a link here to a nice sort of visually rich illustrated tutorial if you want to learn more about how these work. All right, so another key takeaway point that I really want to make sure everybody comes away with this from is that geometry representations and network architectures are really tightly coupled. That basically, once you pick a geometry representation, you've really got to sort of tune a network architecture for that. So I mentioned with images, we can basically reuse the network architectures from 2D vision. Here's some examples of people doing that for a bunch of different analysis tasks and even a synthesis task. 3D grids, again, we can just extend our 2D grid methods to work on them. The one noteworthy thing to mention here is that you can often be more efficient by developing special network architectures that work for adaptive grids, things that place less memory where there just isn't stuff. So things like octrees, I've left a couple references here for analysis and synthesis networks that do this. CAD representations, again, there have been networks that have been proposed for how to analyze BREPs, networks proposed for how to synthesize the sort of procedural programs that produce these things. Not a lot of time to talk about them, but I'll leave these references here. What I really want to spend the last 5-ish minutes, hopefully I have enough time, to talk about is these point clouds and meshes, because this is where I think the most and the most influential kind of architectural innovation has been happening, because these look pretty different than other kinds of data that exist in other fields. So I want to briefly go over an example of each of them. I hope I have time for that. So kind of the first point cloud architecture that's worth talking about is PointNet. This was sort of the original architecture that was proposed for how to natively process point clouds. And so the way that it works is we start with our set of input points. So here we have n points in a point cloud, so we can represent that as an n by 3 matrix. And ignore this thing for now, this box that says input transform. It's not super important. Really what's happening is we have every point is independently processed by one of these multi-layer perceptrons. We have this stack of these linear layers with these nonlinear functions in between them. Again, ignore these blocks that say input and feature transform. They're not important now. But hey, we process the points, again, independently by more MLPs, right? This is why they're called deep networks. We're stacking layers of parameterized processing. Then finally, here's the interesting part. We compute a global descriptor of the entire point cloud by taking an element-wise maximum across all of the dimensions of these feature vectors. And finally, I'm revealing this now. We're using this network to do classification. I have one more multi-layer perceptron, which maps this global feature into another vector of numbers, which we can then interpret as the log probabilities of each class for this particular object. OK, so the key idea, what's really interesting about this network, is it basically says we're going to combine individual or local processing of each point into some higher dimensional feature space. In this case, we go from 3 up to 1024. And then combining these per point features using some order invariant function, like maximum. You could also have used average or sum to produce this global feature descriptor. And this was the key insight at the time behind this paper, is that this order invariance was really key because the points in a point cloud are not ordered. You wouldn't want to train your network on a bunch of point clouds that have one particular ordering and then find that it didn't work on another point cloud. So that was sort of the key thing here. Now, I did elide these details about these transforms, what these are doing. Basically, these are optionally transforming the input points and these intermediate feature vectors by some sort of matrix that gets predicted based on the input. And it's predicted by this thing called this TNet here. The TNet, what is it? It's really just a smaller point net that just doesn't have these transform blocks in it. And the intuition is that maybe if we apply these learned input-dependent transforms to our data, it might help canonicalize the data in some way, bring it into a common sort of coordinate frame such that it will generalize better when we apply it to new data we haven't seen before. And if you look at the original PointNet paper, they do show empirically it leads to slightly better performance. But I like to think of this as an optional step. It's not really a core part of the architecture. And they also show in the paper that you can use this for segmentation or other local analysis tasks. It's not just restricted to classification. The idea is that basically at this particular stage right here, they take this global feature, they basically smash the pointwise feature and the global feature together, and then they continue to process them independently to get whatever local signal they're trying to predict at the end of the day. And the intuition here is that, well, if you combine the local point features with the global features, then perhaps in some way that individual pointwise processing is now context aware of where does that point sit in the overall shape, because it has some view of the overall shape as well. So yeah, you can use this. We can segment 3D point clouds using it, both complete point clouds and incomplete point clouds, and it works reasonably well. There have been some innovations since then. Some more noteworthy point cloud networks include DGCNN, which is basically using a convolution-like layer for this. And of course, people have also tried to apply transformer-like architectures to points as well. All right, I'm running a little bit behind, but I am going to spend the time to talk about this because I do think it's important to talk about neural net architectures specifically for meshes. So I'm going to talk about, again, a somewhat early example of this architecture called MeshCNN. And the key idea here was defining, again, this is a convolution-like network. They had to define this convolution operator, and they chose to define it on mesh edges as opposed to vertices or faces. The reason for this is that if we have a manifold mesh that does not have any boundaries, no open holes in the surface, every edge always has exactly 4 neighbors, and these neighbor edges in this kind of fan structure. And so we know that we can define a sort of a fixed size convolution kernel that always has 4 weights, 5 weights in it, E, A, B, C, and D. And it turns out that we can use the winding order of the triangles, basically moving counterclockwise about the normal direction of that triangle, to always define a consistent ordering of these edges, which is useful. We're going to define some features that are going to be the input features to this network. Every edge will have these 5 input features. It'll have the dihedral angle between the 2 adjacent faces. It'll have the 2 interior angles of those vertices that are opposite. And it'll also have the ratio of the length of the edge, so this edge right here, to the perpendicular lengths of these 2 faces. And finally, we define our convolution operator. So what is this? Again, it's just a weighted sum of E's feature vector. But instead of taking a weighted sum of the feature vectors for A, B, C, and D, we actually first compute this vector, which is composed of all of these different sums and absolute differences of AC and BD's feature vectors, which is kind of a weird thing to do. But the reason they do it is that then it doesn't matter how the 2 incident faces of E are ordered. They did this, again, clever trick, just like PointNet did. These order invariant functions, these sums and absolute differences. You can take a while. If you look at this, you can convince yourself that it does not matter if the way that the edges come into this function are ordered as A, B, C, D or C, D, A, B. Either one, it'll end up being computed exactly the same. And so it doesn't matter what order my faces are listed in my mesh, as long as I have them, consistently, as long as I have a consistent winding order, everything will be fine. OK, and just like PointNet aggregates these local features into global features, MeshCNN also has a mechanism for gradually aggregating local features into increasingly global features by this mechanism of edge collapses, where they basically can take an edge, collapse it, and then the new edges that get produced are their features become the average of the two edges that got collapsed to produce those, or actually all 3, A, B, and E, and in this case C, D, and E. And there is a mechanism to sort of undo this pooling by reversing edge collapses, which they use for segmentation, not as important for classification, but you can look at the paper for more details on that. And so they show examples of things like segmenting human body meshes and being able to classify different shapes. Again, operating directly on the mesh representation, which is pretty cool. Some other noteworthy mesh architectures that I think are worth looking at fairly recently. So DiffusionNet, this is an interesting one. Instead of defining discrete convolution kernels on the surface, it uses actually a continuous diffusion. And I don't mean diffusion in the sense of diffusion generative models. I mean in the sense of the solution to the heat equation. Basically continuous diffusion to propagate features across the surface. The really cool thing about this is that it is agnostic to the discretization you use. You don't have to have meshes triangulated in a consistent way. You can train it on very coarse discretizations, apply it to meshes that are very finely discretized, or vice versa, and it still works. And then also, again, I should mention at least some transformer-based model for meshes. MeshGPT, which I showed earlier, they present this in the context of synthesizing meshes by generating sets of vertices and faces. But actually, the core architecture could also be applied to analysis tasks. I haven't seen anyone do that yet, but it would be interesting to see how that compares to these convolution-like architectures. OK, so that wraps up my brief discussion of neural net architectures for geometry, which means we've talked about, at least at a high level, the answers to all of these questions, which means we are finished with my part of the course. So only a few minutes late. So at this point, we'll take a quick 5-minute break, and then we'll come back.
OK, hello everyone. Welcome back from the break. In the second half of the talk, I'm going to dive into one specific application of learning to geometry, and that's neural implicit shape representations. So in Daniel's part of the talk, which we just saw, Daniel talked about how we can do different geometry processing tasks, or different geometry processing tasks that we can solve with deep learning. So for example, we talked about editing, synthesis, and analysis type tasks. Now we're going to look at how we can actually represent the geometry itself with neural networks. We'll talk about neural implicits, where instead of representing geometry with, say, a triangle mesh or a point cloud, we'll directly represent the geometry by the weights of a neural network. So the goals of this part of the talk will be to learn about what neural implicits are, how we use them, and also when and when not we should use them.
OK. So we're going to finally talk a little bit about
the important techniques for working with neural implicits. And I'm hoping that even if you don't know much about implicits or about neural networks, you'll be able to learn enough from this talk that maybe you could use these representations in your own research. OK, so before we talk about neural implicits, I'm first going to talk about a very classic representation in graphics, which is implicit surfaces. And I think this is important to spend some time on because all the techniques that people have used for implicits for years and years are also really important for working with neural implicits. So implicit functions are just kind of a topic from math. We can define, or we call a function explicit when it kind of generates points on a surface, like this formula for a line segment there. And on the other hand, we can call a function implicit if it kind of defines a surface through a set of points that satisfy an equation. So in this example, this circle is defined as the set of points where this equation, x squared plus y squared equals r squared, holds. We can view that same example in another light, kind of, as viewing the implicit function as a map from some spatial coordinates. Like here, it's the plane, R2, to a scalar. And we can then get a surface from this implicit function by finding the set of points where this function equals some value c. And you can see here different values of c. These are called c level sets. And usually we care about a specific level set, the 0 level set, and we usually kind of treat that as the surface we're representing. Kind of throughout this talk, I'm going to be showing a lot of examples in 2D, like this one. But this is just because they're much easier to draw. Right? This stuff all is also applicable to 3D, and that's where we usually use it in graphics. So implicit surfaces have a really long history in graphics. In fact, they've been around kind of since the beginning of graphics, way back in the 70s, or I guess graphics is a bit older than that. But yeah, this paper here is an early example. It's one of the first to use implicits for modeling using CSG operations, which we'll talk about in a second. I think it's really cool at the beginning of this paper, the author Ritchie mentions that representations of, or the problem of representing a shape, the shape of a 3D object is still an important problem in computer graphics. And in fact, this is a very poignant observation since we're still talking about that in this very talk today. After kind of this early work, there was a lot of work in modeling with implicits kind of in the 80s and 90s. Jim Lin was the first person to render non-analytic implicit functions. This is kind of from that original paper. He actually developed this technique because he was trying to visualize DNA molecules for a Carl Sagan TV series, which I thought was very cool. So he calls this blobby molecules. And there was a lot of work on modeling implicits through the 80s and 90s under many different names, like metaballs and soft objects. I don't have time to talk about this now, but it's a very cool, like, historical field, so I would recommend looking into it if you're interested. All right, now I'm going to talk about some of the kind of most important techniques to have in mind when you're working with implicits, including neural ones, which we'll get to later. First, First, I'm going to talk a little bit about CSG. And so when we're talking about implicits, we usually mean functions that are kind of well behaved enough so that the inside and outside is well segmented, and the inside is negative and the outside is positive if we're considering the surface as the 0 level set. And so if we have a function like that, determining whether a point is inside or outside an implicit is super easy. It's just checking a sign. And this is one of the really great advantages of implicits that make them useful for working on graphics tasks. Specifically, because this inside-outside determination is so easy, constructive solid geometry operations, which are things like unions, intersections, and differences, are really easy to perform on implicits. And in fact, we can kind of write these very simply with max and min functions. The max of two implicit functions gives their intersection, and the min gives their union. CSG operations are really powerful because they let you model super complex objects just from like taking these compositions of primitives. For example, this amazing snail is modeled by Inigo Kriles out of implicit functions. And if you're interested in kind of this SDF art, you should definitely check out his blog. It's very cool. Yeah, let's talk now about kind of the different types of implicit functions we have. For a fixed surface, like this one that's the union between a square and a circle that I'm showing here, there's lots of different valid implicit functions. There's simple ones, like this indicator function, which is a simple discontinuous implicit function that takes one value, say -1, when we're inside the function, and one value, say +1, when we're outside the function. Often the actual values you choose are different in practice. There's also a very special kind of implicit, which is very structured, called a sign distance function. I'll define what that means now. So a sign distance function, which we often call an SDF, is a function where the absolute value of the implicit function gives the distance from that point to the point on the surface. So you can see for that point x way up there, f of x, the implicit function evaluated at x, is going to give us this distance that we can see there to the closest point on the surface. We care about SDFs because they have a lot of nice properties. For example, if you're at a point like x1 here, and you walk directly away from the surface for some distance, say to this point x2, the function value of the assigned distance function should have increased by the same distance that you traveled. Another way to say this mathematically is that the norm of the gradient is 1 for an SDF, and this is called iconality. You can also see the iconality property through the isolines of a surface. Notice that they're evenly spaced, and this is another way to see iconality of a function. So since SDFs are so structured, they make kind of the reason that we like them is because they make many downstream tasks way easier. Here are some examples. We can really easily do surface offsetting just by adding a value and like taking a different zero level set of a surface. We can also we also often want to use SDFs for kind of simulation tasks because we often have to answer questions about how far apart two objects are. So in this example of the cloth simulation, if we represent the sphere the cloth is colliding with as an SDF, we can really easily find the distance the cloth is, or a distance a point on the cloth is to the SDF by querying, just querying the field. And also, SDFs make kind of formulating many geometric quantities easy. There's kind of some that come naturally from this function. For example, the surface normals are just the gradient of the SDF, since it's iconal. And then also, the mean curvature at the surface can just be derived by taking the Laplacian of the SDF. But there is a big problem with working with SDFs, which is that this distance property, which gives us all this great structure, is really difficult to maintain. So for example, a lot of editing operations that we do with fields doesn't maintain this distance property. For example, CSG operations, which we just talked about as being super important, if we would do like some sort of anisotropic scaling or surface offsetting, these will all destroy the distance property. And you can see in these examples here that are kind of real-world SDFs, often will kind of have a function that's kind of close to an SDF, but because it was modeled with like these real-world things that destroy the distance property, it's not going to actually be an SDF, as we can see from these isolines, which are not evenly spaced. So there's another class of functions called conserved SDFs, which is kind of a relaxation of the SDF property in a way. Sometimes people call this approximate SDFs as well. Here, we relax the requirement for the distance property to like a conservative distance property, where instead we require that the absolute value of the function is less than the distance to the closest point on the surface. Conservative SDFs are nice because they're often much easier to maintain. Certain editing operations do maintain this conservative distance property, but of course they don't have the same or they can't be used for all the things that SDFs can be used for, because we can't really guarantee we can't guarantee that the values are actually the real distance. They're just some bound. But one case where we can use conservative SDFs is for kind of a classic way that we render implicits called sphere tracing. This was introduced in 1996. And yeah, this is, I guess this is, just to be clear, this is a very important topic in working with implicits because you often need to render them. And so, yeah, sphere tracing works for any conservative SDFs, but it has much better convergence for kind of a true SDF. And it's going to tell us how to intersect a ray with our implicit surface. So I'm going to give a quick walkthrough of how it works now. If we have this ray that we want to trace, the eye is at the point. This is the origin of the ray, and we want to see where the ray intersects the surface if we go in that direction. We can, at the origin of the ray, obtain the distance from that point to the closest point on the SDF. And this gives us a mount we can walk along the ray where we know that we definitely won't collide with the surface. And so we walk that distance along the ray, we get to a new point, and we can actually just repeat this procedure at that point, and continuing this until we reach some very small distance, we'll obtain the collision between the ray and our implicit function. This gives you a way to render implicit functions. Another task that we often want to do is surface extraction. This is where you want to get a mesh from your implicit function. This is very commonly done with marching cubes, which is kind of an algorithm that dates back to 1987. And the main idea of marching cubes is you kind of start with a grid of values where you've evaluated your implicit function or where you know your implicit function. And marching cubes is going to give us a way to decide where the surface should be in each of the grid or voxel cells, voxel if we're working in 3D. Concretely, the way that we do this is we kind of look at each grid cell. We determine if each of the points in the grid is inside or outside the surface. And then we can figure out how we should draw this, we can figure out how we can draw how the surface would pass through each grid cell, kind of based on these cases where the points around the cell are kind of mixed inside or outside. We can then kind of go through the grid and just determine which case applies at each grid cell, and that lets us build a surface like I've built here for the star. In 3D, this is exactly the same. We just have many more cases to determine, and so we just end up with a big lookup table in the code. So marching cubes is very commonly used, but as you can see, it often leads to kind of undesirable errors on the surface, especially if you don't use a very fine grid. So there's been some recent work that I think is very cool improving it. I don't have time to go into detail, but one technique is Ritchie et al., which talks about how to use kind of all the distance information that you have in an SDF to get better surface extraction. And there's also been techniques that have tried to use, have kind of learned priors from data in order to get better reconstruction. Finally, I'm going to talk a little bit about when we should use implicit representations over explicit representations. So kind of this determination is very problem dependent in general, but we can kind of think about, at a general level, what kind of questions we want to ask. If we want to ask questions about points in space, implicit functions are good at answering these. For example, if we ask, is this point inside or outside the shape, implicit functions can answer that kind of naturally. On the other hand, if we want to ask questions directly about the surface, like what's the total surface area or the total perimeter, those are questions that explicit representations are really good at answering. And kind of at a higher level, these benefits also lead to kind of like high-level properties that are nice. For example, implicits are always kind of watertight by definition. And as we discussed, one of the big pluses is that it's really easy to perform CSG operations on them. On the other hand, explicit representations are often or kind of usually faster than implicit representations. And also in geometry processing, we often care much more about exactly what's happening on the surface. So explicit representations are often useful for those kinds of questions. Finally, I just want to highlight one benefit of implicits, which I think is often very important, especially in neural implicits, which is that in implicit representations, changes to the topology of a shape are continuous. And so this is really useful when we want to perform various inverse tasks, like this one where we're trying to reconstruct the shape. All right, and you can always convert between implicit and explicit representations. We talked about using marching cubes to get an explicit representation from an implicit representation. And you could do something like computing the distance at every point to get a SDF from an explicit. But it's important to consider that converting representations like this leads to introducing some error. And so it's really important to pick the representation that works well for your problem to kind of, to make sure that you're not converting if you don't have to. All right, so we've talked a little bit about this. We've talked a little bit about kind of the basics of implicits, but now let me talk a little bit about how we actually represent these functions on a computer. So we've already seen that some implicits, like this circle, for example, can be represented through a simple mathematical formula. And when we represent implicits like this, we call this an analytic representation. We can kind of write analytic representations for lots of different shapes. For example, on Inigo Krilis's blog, he has some cool lists of different analytic formulations for 2D and 3D, including the star. But as you can see from the star, which I've written the code up there, the star is very kind of complex. And so as you want to represent more complex shapes with analytic representations, often it becomes slow to compute. And also, you can always find an analytic representation for kind of whatever shape that you might want to represent. And so instead, it's common to represent implicits as values stored on a grid. If we make the grid fine enough, we can represent any shape at all, like this cat, which is represented very well. But there's an issue that grids don't scale very well, especially as we kind of increase the dimension of the implicit we want to represent. And so there's lots of solutions to this, like adaptive grids, which I won't get into detail here. But kind of the general idea of those is that we can use less resolution far away from the surface that we want to represent. Instead, I'm going to talk about kind of a view of grid-based representations that might seem a little bit weird, which is that we can just think of grid-based representations essentially as a function. And so we can think of this function as mapping a point in our domain to a value. And you can define this function kind of in this way where you just think of figuring out which point or which grid cell the point lands in, and then you return the value stored in the grid there. And so kind of in this function space picture, this function is parameterized by the grid values, which I'm denoting as W here. But we could actually kind of generalize this to representing our functions with with any function space. For example, here is the kind of very classic function fitting example of the function space of multivariable polynomials of different degrees. You can see this simple setup I have doesn't work very well, but there's lots of variations to kind of the function space we use, which can give you, or which can be really good at representing representing implicit functions. All right, so with that, we've kind of talked about the basics of implicit surfaces. This is a representation that's existed in graphics kind of practically forever. And now let's talk about neural implicits. And this is going to be, here we're going to essentially just use neural networks as a function space to represent the implicit functions that we're working with. So we talked a bit about what neural networks are in Daniel's section, but I'm going to talk specifically about the neural networks that we use to represent neural implicits most commonly. And these are usually multi-layer perceptrons often with ReLU nonlinearities. But if you don't know anything about neural networks, don't worry, we're going to talk about that now. And the high-level idea is just that neural networks are kind of some function space in which we can fit our implicits in. And so in the case of neural implicits, our function is going to map from like some n-dimensional coordinates, like 3 or 2D, to a scalar. And we have kind of this construction where our function is some like linear layers stacked on top of each other, which Daniel already mentioned. This is just a linear function applied to our input. And these entries of our matrices are kind of the parameters of our function, like the parameters of the polynomial we talked about before. And here I'm just using theta as a shorthand to represent all of these parameters. Between our linear layers, if we had nothing, kind of this whole thing would just be a single linear function. And so instead, we add some nonlinearities, which we often call activation functions in machine learning. And these are element-wise functions. And some common ones to use are tan, or hyperbolic tangent, or sigmoid. And kind of the most commonly used one, I think in general, but especially in neural implicits, is ReLU, which stands for rectified linear unit. And this is just a linear function right there, which where all the negative values are clamped to 0. And so kind of at a high level, we've just discussed what a ReLU MLP is. And for specifically the case of neural implicits, we'll have kind of an input layer that's mapping from the dimension of our space, like 2 or 3D, to some hidden size. And this is going to be kind of the dimension of the layers inside our network. And then we'll have some output layer, which maps from kind of whatever the size of like the layer before it is to a scalar, since we're fitting an implicit. And then we have these collection of hidden layers. And the number of hidden layers and kind of the size of these layers are going to be hyperparameters of like this procedure. Yeah, and I guess just the important takeaway from this section is that neural networks just provide us a function space. You don't even need to think so much about what the function space is, but we just have some parameters, theta, that like parameterizes the space. And so the idea of neural implicits is to use this function space to represent implicit surfaces. And here I'm showing some of the early papers that proposed this idea. They're all kind of from around the same time, and they look at different types of implicit functions, like indicator functions or SDFs, and apply them to different problems. And I don't have time to go into detail about them, but you should check out if you're interested. Yeah, now let's look at kind of a very basic problem we can solve in neural implicits. We want to overfit a neural network to represent a specific, like, single implicit function. So here, we're given some observations of the implicit, a set of points and their corresponding observed values, which you can see visualized here. And yeah, maybe you can see these observations often come from some underlying implicit. Like maybe you guessed I was showing you points that came from the implicit function of a star. And then the way that we actually fit a neural network is we want to kind of find the neural network that best fits these observations, minimizing over the function space. And so here we're minimizing over theta, which are the parameters defining our neural network. And we want to minimize some loss function, for example, this square distance between what the neural network thinks the implicit function value should be at some points and the actual value that we observed. And in practice, when working with neural networks, we usually would use stochastic gradient descent to solve this problem. And often we call this problem training, but this is actually just optimization if you're familiar with it. Also in practice, this kind of stuff is very easy to implement. So you probably can't read this, but here I'm showing kind of all the code you need in PyTorch, a common library, to implement the stuff I just said. This little piece of code is defining the structure of a ReLU MLP. And this little piece of code is just a training loop to fit this MLP to some implicit function. So this is actually like really easy to implement in practice, which I think is very cool. All right. Now we're going to talk a little bit about why you might want to use neural implicits and why you might not want to use them as well. So I think one question you might be left with after we talked about kind of this arbitrary seeming set of functions is whether this is actually a good function space. And there's a few things we can say about that problem. For one, there's kind of a set of theorems that people often talk about in machine learning called universal approximation theorems. For example, there's one that says that a multi-layer perceptron with one hidden layer of infinite width with ReLU nonlinearities can represent any continuous function. So this tells us something about how kind of this general structure of functions seems to be able to represent a lot, but with these few caveats. And then in practice, people have shown in lots of papers over the year that you can represent very complex geometry with neural implicits, like this crazy complex room maybe. But I think it's important to note that the theory behind what we've seen here doesn't really describe networks in practice because we actually are not using networks with infinite width like this theorem requires. A second reason, or a second kind of benefit of neural implicits is this fact that neural implicits have some ability to kind of adaptively use the parameters in kind of spaces that are or kind of in the geometric space that's more important. But it's important to note this kind of depends on choosing a good loss function. And you can think of this like in a simple grid. You kind of the parameters are laid out in this very regular way geometrically. We can't decide where they go, but in the neural network, kind of they're going to be used wherever they can be to best minimize the loss. And here's a little experiment demonstrating something along these lines, where I can represent the star like I do on the left, I think it is for you, where I can represent the star like on the left with this grid that's 50 by 50. You can see the grid is actually like, this is a pretty small grid. And so even if I kind of compute, or even if I plot it with like linear interpolation and try to get the zero level set, I'm going to end up with something that doesn't look so good. See in the blow for the grid, we kind of lose the corners of the star. If I instead fit a small neural network, like this one that's on the right, I think, for you, hopefully, which this neural network has the same number of parameters as my grid. It actually has slightly less. But because I train this with a loss function that kind of cares more about values near the surface, and I'm able to obtain a really nice fitting of the surface. You can see I got kind of pretty sharp corners for my star. And so this kind of demonstrates this idea that neural networks have this ability to kind of place their parameters in places that are more important. OK, but I'll just leave, or before I move on, let me just mention a caveat kind of for these last 2 points that I just talked about, which is that we found that kind of neural implicits and also in other places in ML, we can do like a lot of really amazing things with neural networks. But kind of our understanding of why exactly these things work so well with neural networks is a bit behind kind of the things that we've actually found work really well. So I think there's some more research into the theory that needs to be done here. Okay, finally, I think the most important benefit of neural fields is that they're trivially differentiable, which means that they can be used in a whole host of kind of problems and kind of just naturally slot into a lot of applications. For example, here we can use neural implicits to first learn kind of a space that represents the geometry of cars, and then from a single view of the car, we can reconstruct the geometry of the entire car. This is showing that. And then we can also kind of embed our geometric objects in like something like a learned latent space. And then if we interpolate between, and then this lets us kind of naturally interpolate between two different points in this latent space, which gives us an interpolation of the geometry between those two different points. And then kind of in general, many graphics problems can be formulated as a loss function, which can be used to train a neural implicit that solves that graphics problem. So I thought this paper was really cool, which performs topology optimization using neural implicits, because we can formulate the topology optimization problem as a loss function, which we then minimize. Kind of at a general level, I would say neural implicits are really good for solving lots of different inverse tasks that involve learning from data, and they also just kind of naturally slot in really well with the ML toolbox. And I think these might seem like kind of small advantages, but this is really what's made neural implicits such a powerful representation. They're really easy to solve like so many important problems with. But we also have to talk about why we might not want to use neural implicits. So for one, there's often an issue with imprecision in neural implicits. The properties that we want to enforce are only ever going to hold through soft losses. And that means if we want to constrain something, like maybe we want to constrain a neural network to have the SDF property or to reconstruct some data, these are going to be implemented through a loss function, which just holds kind of softly at optimality. And this can lead to issues like the very common one that we lose sharp features in our neural implicits. And if you have an application, and you also it's kind of often hard to exactly quantify the amount of error that comes from this issue of the constraints only holding to soft losses. And so this is a big issue if you want to perform applications which require guarantees for maybe applications with safety concerns like medical applications or toolpath planning. Secondly, since the geometry of a neural implicit is stored in the weights of a neural network, many downstream applications can be kind of difficult to perform with them. For example, editing is one. If we try to simply change one of the weights in our neural network to edit a neural SDF, we'll find that this leads to very unintuitive changes in geometry. Finally, and again, perhaps most importantly, I think it's very important to always pick the right representation for your problem. I think I've already said this, but I'll just mention it again. So this means that if our problem isn't well suited for implicits, maybe it's better to use explicits for, probably neural implicits might not be the best choice. And of course, we also just talked about a few reasons why a discrete representation might be better than a neural representation. So it's always important to consider. With that out of the way, I'm now going to be talking about a few kind of details that are important to know when you're working with neural implicits. So likely, if you try to use neural implicits for your own research, you might run into these details. So hopefully it's important, or hopefully it's helpful to kind of hear about them now. One issue that you very often encounter when using standard techniques for fitting neural implicits is that they have a lot of difficulty capturing sharp features. And there's kind of two main techniques that are often used for solving this, both in 2020. And they both work pretty well. The kind of general idea of both of these papers is to somehow give the network a way to see the high frequency details of your data. But I'll talk about specifically a little bit about how they work now. So in kind of the first paper, Fourier features, instead of just passing into the network the spatial coordinates of our input, this paper suggests that we compute this Fourier feature mapping of those input points. And this essentially just means, or in practice, this just means calculating some set of randomly scaled sines and cosines of the input point. And you can see this works really well in practice to recover sharp features like this dragon. The top is showing the kind of fit of this 3D shape with a ReLU architecture, and the bottom is showing the fit with this Fourier features method. Another way we can do this is with this paper called Siren. Unlike Fourier features, this is only changing the activation functions in a network. And they simply say that instead of using ReLU activation functions, we should use sines as our activation functions. And this gives the network some ability to kind of reason about details at different scales. This is a really easy change to make, but if you're trying to use it in practice, it's important to be aware that you also need to make sure that you're initializing your network properly. And they talk a little bit how to do this in the paper, but yeah, be aware if you're trying to implement it. Another kind of important topic is the idea of hybrid discrete continuous fields. This is kind of a way that we can, I guess the general motivation here is to somehow, maybe we can figure out how to get the best of both worlds between storing data in a voxel grid, where we have some idea of locality, and we can take advantage of the spatial structure. And we want to also get the benefits we talked about of neural fields. And so the idea here is to learn some spatial features at grid points. And then instead of having a neural network that just maps from an input spatial point to a scalar, we instead have a neural network that takes both the spatial point and some features that we interpolate from this grid. And then from that, it predicts the scalar. And so this gives the network some way to kind of use this locality. This has been used in practice in this instant SGP paper, which uses the same kind of strategy, but also at multiple resolutions, kind of like traditional octrees. And they have lots of performance optimizations, and with these, they're able to achieve this kind of effectively instant training of neural fields. And so these kind of hybrid discrete continuous fields are really good if you want something that trains faster and also has kind of more small details. Finally, it's also really important often to consider how you choose sample points for tasks where you need to do that, like for overfitting a single shape, or kind of fitting a network to a family of shapes as well. So some general principles behind like how you should do the sampling is described in this paper on the effectiveness of weight-encoded neural implicit 3D shapes. But kind of as an overview, in general, we care mostly about the reconstruction quality of our implicit near the surface. And this means that we want to kind of bias our loss to penalize deviations near the surface more. And you can achieve this biasing instead by changing how you sample your points. And so if you instead import and sample near the surface, for example, with rejection sampling, you can obtain you can obtain kind of better reconstruction of your surface. And you can see this example here, where if I use import and sampling, I can obtain much better surface of Spot, like I can get his ears, whereas they're lost if I don't do kind of a smarter sampling strategy. OK, and then finally, for the last kind of chunk of this talk, I'm going to be talking about how we can perform geometric operations with neural fields, since we are at SGP after all. One general way we can perform geometric operations with neural implicits is to make sure our neural implicits are signed distance fields. Because as we talked about at the beginning, if you have a signed distance function, this function that encodes the distance from every point to the closest point of the surface, you have a lot of structure that makes answering many geometric queries easy, like these offset surfaces or asking about the curvature. But this then leaves us with the question of how do we make neural implicits, or how do we make sure our neural implicits are SDFs? And the kind of general way that or the general technique we use to answer this is to add a regularization term to our loss function, which ensures that which encourages the neural implicit to become an SDF. And kind of a very, often used way to do this is with the iconal loss. So this loss function just takes computes the gradients everywhere in the field. Easy to do because your neural network is differentiable. And then it computes the difference of the norm of the gradient, or difference between the norm of the gradient and 1, which I'm plotting here with red being the higher loss. And you can see, so in these regions where the isolines are not equal, which are regions that are not iconal, this loss gives us higher values. But there's actually kind of a problem with using the iconal loss, which is that not all implicits are actually iconal, not all SDFs are, not all iconal functions are SDFs. Apologies. One example of where we might run into this issue is when we're performing CSG operations, like this one I'm showing here, that makes this tree and moon. And we talked about before how CSG operations are a really important technique in implicits that are often used for modeling. The issue with performing, or kind of the issue we run into, is if we perform CSG starting with two SDFs, for example, this intersection between the two circles, which gives us the moon. Even if we start with two SDFs, the output isn't actually going to be an SDF. As we can see here, if we look at the distance value in this point kind of in the resulting field, this does not give us the closest point, or this does not give us the closest point or the distance to the closest point on the surface from that point. It's actually encoding the distance point, it's actually encoding the closest point to a surface that was kind of in the original shapes we intersected, but is no longer in the intersected shape. And so I call this type of function a pseudo-SDF. And kind of we define pseudo-SDFs to be these fields that are iconal, which we can see from the kind of fact that the isolines are evenly spaced, but they do not obey the distance property. And if we look at an iconal function, like this one of the tree scene, which I made with CSG operations, and we compute the iconal loss on this pseudo-SDF, we're going to see that we actually get zero loss everywhere, because pseudo-SDFs are by definition iconal. And so in a recent paper, which is my work, we formulate CSG operations and swap volumes, which is a related problem to CSG operations on neural SDFs. And kind of the key problem we had to solve in this paper was this pseudo-SDF issue that we had these functions that were iconal but were not SDFs. And so we introduced a loss which we call the closest point loss, which, unlike the iconal loss, is able to detect pseudo-SDF regions. And so it gives us a way to fix these functions with these pseudo-SDF issues. And so I'll walk through how we formulate it now pretty quickly. So if we consider this exact SDF of the moon, and we sample some random points in space, we can compute the distance from those points to the closest point on the surface by just evaluating their value in the SDF. And if we take the gradient of the field and negate it, we get a vector that's norm1, and it points directly towards the closest point on the surface if we're outside, and directly away from it if we're inside. And so if we multiply this direction with the sign distance value, we get a vector that goes directly from the point to be sampled to their closest point on the surface. If we then walk along that vector, we get the closest point map, which is a kind of well-known object in the study of SDFs, and gives us a way to map points directly to the closest point on the surface. If we were to instead have started with a pseudo-SDF, like this one of the moon, which I made through an intersection, and we again perform kind of this closest point map procedure, we find that this leads to points that were in the pseudo-SDF regions of the original shape, not mapping directly to the surface onto the closest point map. And so to again we can kind of use this observation to construct a loss function for pseudo-SDFs by computing the value of these mapped points in the original function. And if we have an exact SDF, this is going to be 0 everywhere because all the points mapped exactly to the boundary, the 0 level set. But in a pseudo-SDF, kind of these pseudo-SDF regions will have points that don't map directly or don't map to 0 and so have loss. And so yeah, if we this procedure then gives us a way to construct a loss function which penalizes regions that are pseudo-SDF. So as kind of an overview, we have these two losses that that together prevent these pseudo-SDF issues, and they also regularize the problem really nicely so that we can get a true SDF. And if you're solving a problem where you care, where it's really important that you have an SDF, it's important to kind of use this closest point loss to prevent running into pseudo-SDF issues. But if your problem, I just want to note, if your problem is formulated in some way where you kind of know that you're not going to get near these pseudo-SDF minima, it's often OK to just use the iconal loss, and it can give you better performance. So kind of overall, these ideas gives us a way to work with neural sign distance fields. And as we discussed, this is really useful because SDFs have a lot of like natural geometric, or have a lot of geometric operations that we can formulate really naturally on them. But as we've just seen, maintaining the distance property can be really difficult. And so even though this can be hard, there's lots of methods that have been developed using neural implicits. For example, this paper from Yang et al. Up there, which shows how we can perform certain geometry processing tasks, like smoothing and sharpening, directly on neural SDFs. And also this popular paper, News, which talks about how to do the reconstruction tasks. In this paper, which is like not very geometry processing-y, but they still use SDFs because they really need distance guarantees in their method. But there's also some alternatives to using SDFs for geometry processing with neural implicits. I'm just going to mention one here, which is this really cool paper from Sharp et al., which demonstrates how you can form lots of queries, like intersections, closest point queries, or ray casting, with general neural implicits, not SDFs. I don't have time to talk about the technique, but kind of the general idea is that they use interval analysis, which estimates whether or not an interval directly crosses 0, but they apply this directly to the neural network. OK, finally, let me quickly conclude. So we just saw how to work with the kind of very classic representation of implicit functions. We then saw how one way to encode implicit functions is through this neural network function space. And then we talked about some techniques that are really important to know when you're working with neural implicits. And finally, how we can use neural implicits for geometry processing. I'll just finish by describing a problem on neural implicits that I think is really important, which is that we've talked about how picking the right representation is a really important thing when you're working kind of with geometry. And among many considerations for picking the right representation is picking one where you don't have to transfer between your representations, because this leads to loss and can make certain tasks like really hard to solve. And so neural implicits have been becoming a much more widely used representation. But because of this, I think it's very important to think about, kind of from the geometry processing community, how we can formulate core geometric operations directly on neural implicits, so that we can work kind of entirely in the neural world instead of having to sometimes extract our surface and refit to be able to actually perform certain geometric operations that maybe we don't know how to apply directly to neural implicits, but only know how to do on, say, triangle meshes. And so I think it would be amazing if someday we could work kind of, or perform any geometry processing tasks directly on neural implicits. All right, that's all I have. If you want to see the slides for either my section or Daniel's section, those are both, you can take a picture of these QR codes here. And yeah, thank you for listening, everyone.